Now we will see a practical example of calculation of a fixed tube sheet exchanger. Let's take a fixed tube sheet exchanger that we have on a file. This is NEN1, and let's see the characteristics of this exchanger. First of all, we look at the item properties. The item properties say that this is an exchanger. Its name is NEN1 because it is a TEMA type NEN. Type of exchanger is fixed tube sheets. Calculation standard ASME VIII Division 1 edition 2021, the metric edition. Therefore, data units are megapascal and degrees centigrade. Materials are carbon manganese silicium. And let's see a little bit better geometry. Geometry, it's not a vertical item. This is the TEMA type repeated. N is the first channel, E is the shell, and the other N is the other channel. Tests. Hydrostatic test, location, wind is not, and seism is not important. TEMA, yes, this is TEMA compliant, and this is a class R according to TEMA. Let's see which are the operating conditions. The operating conditions are use operating temperature, repeat calculation in uncorroded conditions, and then let's look at the various components. Shell. The shell design temperature is 250 degrees. The operating temperature is 175. Mean shell metal temperature along the shell length is 200 degrees. This is important for the differential thermal expansion between shell and tubes. Shell side design pressure is 25 bar, 2.5 megapascal. The joint efficiency is 1. The corrosion allowance is according to TEMA, 3.2. Shell side, this is not there is no weld overlay, there is no lining, no cladding. Then let's go to channel. Channel, we have 250 degrees as design temperature, 175 as operating temperature. Design pressure is 50 bar, 5 megapascal. Corrosion allowance and joint efficiency are the same as the shell. Tube sheet, design temperature always 250. This 175 is 75 is a little bit conventional. Of course, we should look at the thermal design in order to find exactly this temperature. Tubes, the design temperature always the same, but the mean tube metal temperature is 150. That means that the tubes are colder than the shell, and therefore there is an additional pressure which acts on the tube sheet in the same direction as the tube side pressure. No external pressure. Okay, we just wanted to see. In order to make a design, there is a very simple procedure. So there is the so-called wizard, what we call a wizard. Wizard is an input card which contains all the components of the heat exchanger. First of all, we decide that this is a design, not a checking. And then there are some characteristics. For example, the geometry of the front head. The front end, it's an N-type channel. There is a welding neck flange, it is possible to specify a minimum wall diameter. The inside diameter is 1.5 meter, the channel length is 600 millimeters. Materials are all ASME material according to the specified type. We say that we want carbon, manganese, steel, so you see that the plates are in SA 516 grade 70, etc., etc. Gasket, it's possible to specify a gasket material. The pass partition, it is possible to specify the pass partition, the pressure drop across plate. This is important according to what I said this morning about the general design. Shell and tube sheets, we have one pass shell. The shell material is always the same as the channel material, SA 516.7. Inside diameter is also the same. The rear end, we have the rear end, it's exactly equal to the front end, so same length, same diameter. Materials, gasket, everything. You specify everything, and then when you say OK, the exchanger will be completely redesigned according to the characteristics that I have given on the wizard. Now we look at the various thicknesses. There was also another on the top here that has not been redesigned, it has been taken exactly equal. And now let's look at some component, for example, at the tube sheet. The tube sheet has a thickness of 226 millimeter. Well, it's the forging SA 266.2. If we want to really see what has determined the thickness of this tube sheet, there is a very simple trick that we can use. We decrease of 1 millimeter, 225, and suddenly we get this red warning. Load case operating with a tube side pressure of 50 bar. A shell side pressure is 0. There is a thermal expansion, there is no vacuum. And what has limited the thickness of this tube sheet? The total axial stress in the channel at its junction with the tube sheet. You see, taking out 1 millimeter instead of the required 464 megapascal, we get 464.21. Well, this is the minimum thickness, but we may have some doubt about if really it is the channel which has determined this tube sheet thickness. Why not to try to increase the channel thickness to see if the situation might improve? If we go here on the main shell left channel, okay, we go to the left channel, which has a thickness of 32 millimeter. Well, try to put something more, may 35, and okay, we left channel and then the flange hub, okay, of course, the hub of the flange has been changed because the flange must be connected now to a plate which is 35 and not 32 millimeter. In order to complete this, we can also increase the thickness of the other channel, which is 35 too. Okay. Well, we see now that everything is okay. Also with 1 millimeter less, the tube sheet is okay. But maybe it is possible still to take out some millimeter. 224, is always okay. 223 is always okay. Well, try something more, maybe 200. 200 also is okay. 199, 198, okay. 198 is not okay, so 199. 199, so we have taken out from the tube sheet thickness 27 millimeters, just increasing the channels of 3 millimeter only. Well, of course, these 27 millimeters are probably more expensive from the point of view of cost than the 3 millimeter of the channel, not only because of the material, which is a forging, but you must think that you have to drill this tube sheet, so there are a lot of man hours more due to this additional 27 millimeter. But now let's see what is limiting now. So we try, as before, we take out 1 millimeter. So the problem is always the total axial stress in the channel at its junction with the tube sheet, exactly in the same case. Possibly a further increase of the channel may improve the situation. Well, we cannot go on increasing the channel thickness without looking at the other components, like the flanges that are connected to the channel. Of course, the best solution in this case is to call again the wizard and activate it as checking, and instead of putting 35 millimeter on the thickness, we have 40 millimeter on the thickness on the front end, and the rear end also 40 millimeter. Well, that's a checking, so the 199 has not been changed, but we will change this later. We run again the calculation, so all the components have been now redesigned, and what we see, okay, let's open the tube sheet. The tube sheet is 198, now it's okay, but this was a checking. There is without running again the wither, there is another possibility. There is the possibility of making not in here, not in geometry, but in general here, the design mode, to activate the design mode. The design mode means design the tube sheet thickness, find the tube sheet with the lowest possible thickness. Okay, design complete. Okay, now geometry. Geometry is 158 thickness. We started from 226, and 158 means 26 plus 42, 68 millimeter less. It's a lot of money that we have spared in this way. Well, just make still a small test to see if the situation is always the same. So if it's still the channel thickness which is limiting. Let's take out 1 millimeter as before, and we see that always the channel thickness is limiting. It's really a problem, this one. However, to still increase the tube sheet, the channel thickness doesn't seem to be a nice solution. So it's better to leave the exchanger like that, and to see, so we close this, and we close also the item, and we try to see what happens if we change the standard. So instead of using ASME VIII Division 1, we will see what happens if the design standard is EN 13445-3. Therefore, we open a new item. This item is exactly equal to the previous one, except for the design standard, which is now the EN harmonized standard. In order to be sure about the characteristics, we run again the item wizard, just to check if the characteristics are really the same. We have the geometry materials gasket. Note the materials are still ASME materials. Shell and tube sheets, you have seen that SA 516 grade 70. The tubes are SA 210 grade A1. And the operating conditions for the shell temperature, metal shell mean temperature is 200 degrees, while for the tubes the temperature is 150. This is the case in which the tubes are colder than the shell. We run the wizard. We see that the tube sheet thickness is now 120, more than 100 millimeters less than the tube sheet calculated according to the ASME code. If we want to go to a little bit more in details, we open the tube sheets. We see that there is a yellow warning. Well, this is a warning which is normal when you use ASME materials with the EN standard, because the group to which this material should belong is a group with a higher carbon content, which generally doesn't happen when you purchase the material in Europe. Certainly this will be a material which, according to its analysis, has to be certified according to group 1.1. We go now into the geometry of this item. Tube sheet thickness 120. We want to know what is the reason why the tube sheet thickness is 120. We take out 1 millimeter, as in the previous example. Now we have a red message, error, which is now an error message. In this message, we see that the shear stress of the tube sheet has been exceeded. The problem is really the tube sheet, it's not another component. What we want to do now is to see the behavior of this tube sheet in the case that the differential thermal expansion is reversed. So in case the tubes are hotter than the shell. We come back to the wizard. Let's change the wizard, and we change the operating conditions. So shell, instead of 200, the shell, mean shell temperature, we put 150 here. Shell operating temperature is also 150. The tubes, for the tubes, we take, on the contrary, 200 degrees. Tubes hotter than the shell now. And, okay. We run again the wizard, and we look at the tube sheet thickness, the resulting tube sheet thickness, which is now only 73 millimeters. So the tube sheet is much thinner. Using the same procedure as before, we open the tube sheet, we take out 1 millimeter, 72, and we see that now the limit is given by the tube loads because axial stress in the outer tube row exceeds the maximum permissible buckling stress. Now, the limiting component are the tubes, because the tubes would have a state of compression, so a buckling load, which is given by the fact that they are hotter than the shell. But probably the limit imposed by EN for this thermal buckling is much higher than the limit imposed by the ASME code. Now we come back to the original thickness, which is the right one. We close this item, and we think to have given a little bit a general look on the situation of tube sheets and on the important difference that there are between the ASME standard and the EN standard, despite of the fact that both standards are based on the Gardner method. However, the standard is a standard and you have to follow it. Note that we have used the same materials, so all ASME materials, what is changed is only the design standard. Well, I have finished. I thank you very much for your attention.